Today we are looking at solving systems of equations by graphing, part 2, and we are going to be looking at, again, graphing systems of equations, but we'll be able to look at special cases. We'll be able to state the solution to a system of equations by looking at the graph, and we'll be able to do that exactly and approximately. And again, today we're focusing on special systems of linear equations. So sometimes we will encounter special systems of linear equations. It is possible for a system of linear equations to have no solution, and it's also possible for the system to have infinitely many solutions. So linear systems that have no solutions will be linear systems that have the same slope, which is the rate of change. And these lines, when we graph them, will be parallel to one another, and so they will have no solutions, and that's because they never intersect. Okay, so when we have two lines and they're on the same coordinate plane, that's a linear system. Okay, but if they are parallel to one another, they will never intersect, so they won't cross, they'll never touch, and that means that they have no solution. Then the next special case is when we have linear systems that will have infinitely many solutions. So these are equations that have the same slope and the same y-intercept. In other words, they are the same line. The equations may look different. They may be in a different order. They may be, one looks like it's doubled or tripled as far as the coefficients. But when you simplify it to be able to graph it in slope-intercept form, you'll see that they're exactly the same line. Okay, so they may be written in the same form, or they may be written in different forms. Lines that are equal to each other have infinitely many solutions because they intersect everywhere. So when we're determining whether we have encountered a special system, it is helpful to write the equation in the same form so that we can see if they're parallel or if they're actually the same line. So let's go ahead and take a look at this first example. So the reason we want to put it in slope-intercept form is because then we can see the slope. Okay, if they have the same slope and a different y-intercept, then they will be parallel lines. If they have the same slope and the same y-intercept, then they're actually the same line. So for instance, maybe they were both y equals 2x minus 1. Okay, so let's go ahead and do that. Let's put this top equation is already in slope-intercept form. So let's go ahead and put the bottom equation into slope-intercept form. We'll add 6x to each side, negative 6x plus 6x, that cancels out. So we get 3y equals, and then we know we're working toward getting it in slope-intercept form, so we'll go ahead and put our 6x first and then the 3. So 3y equals 6x plus 3, and then we divide each term by 3. 3 divided by 3 is 1, so we get y equals 6/3 is 2, so 2x plus, and 3 divided by 3 is 1. So y equals 2x plus 1. So we have this equation, y equals 2x minus 1, and then we have this equation, y equals 2x plus 1. Okay, so we're going to go ahead and graph them, but I want you to be able to just look at the equation and see, well, they have the same slope, so we know they are going to be parallel. They have the same slope and they have different y-intercepts, so we know they're going to be parallel. And parallel lines will never intersect, so no solution. But we will still graph it because our instructions tell us to. So our y-intercept is negative 1 for the first equation. Our slope is 2. Okay. And then our next line has the same slope, but a y-intercept at positive 1. Okay, so up to right 1. Down to left 1. Okay, and so we can see that those two lines are parallel. All right, so parallel lines will never intersect. They have the same exact slope but different y-intercepts. So that is the first example of special cases of linear systems. So no solution, parallel lines. Okay, and let's go on to the next page. Okay, x plus y equals 3 and 2x plus 2y equals 6. So if we are just careful, we can look at this, or if we just take a moment and look at this, we can see that if I take this entire top equation and double the entire equation, I can see that these are proportional. All right, so this is going to end up being 2x plus 2y equals 6, which is the same one here. Okay, but I want to prove that by putting them both into slope-intercept form, okay, because you may not recognize that right away, and putting them in slope-intercept form is a really useful way for us to be able to compare. All right, so let's just say that we did not notice that relationship, or maybe they were in a different order, or maybe the factor wasn't quite as straightforward as just doubling. Okay, so let's go ahead and pretend we didn't notice that, and we're going to go ahead and put both of those equations into slope-intercept form because I want you to see how it simplifies down. Just like here, I scaled it up to see that they were equal. Okay, you're probably not going to be doing that right now while you're first encountering these problems. So we want to have a strategy that's going to work every single time. So this is a great strategy. If you're showing me your work that, hey, I noticed these are doubled, so if I were to simplify this one, it would go into that one. Okay, I could have done the reverse here, factored 2 out, but let's go ahead with a strategy that's going to work for every single set of equations, okay? So let's take that first equation, x plus y equals 3. Let's put it in slope-intercept form to get y equals negative x plus 3. And let's take our second equation, 2x plus 2y equals 6. Let's put that into slope-intercept form. 2y equals negative 2x plus 6, and then divide each term by 2 to get y equals negative x plus 3. So we see they are the exact same line, same slope, same y-intercept, and then let's go ahead and graph it, and it's actually the same line, so we just have to make one graph. Y equals negative x plus 3. We'll have a y-intercept at 3. It has a slope of negative 1, so I can go down 1, right 1, down 1, right 1. Just on that diagonal. Okay. It's just hard for me to see that. Okay. Hopefully I'm getting those points pretty close. Okay, and so it's actually just one line. So if I graph the other line, it's going to just directly overlap the line that I just graphed. Okay, so I was slightly off there. I missed the point just a little bit, but there are infinitely many solutions. Okay, and that's because the lines are exactly the same and they will intersect everywhere. All right, next, Team A and Team B are kayaking. So Team A is in a kayak race against Team B. Team A is traveling at 5 miles per hour and is 2 hours ahead of Team B. So Team A, 5 miles per hour and 2 hours ahead. So maybe they got up earlier. And Team B is also traveling at 5 miles per hour. And they're 2 hours behind Team A. All right, and so will Team B catch up with Team A? Well, if they're both going at the exact same speed, and Team A is 2 hours ahead, Team B won't be able to catch up, okay? Because they're traveling at the exact same rate of speed. So no, Team B will not be able to catch up with Team A because Team B will not be able to catch up with Team A. Okay, so those are our parallel lines. Okay, you can envision that. We'll not be able to catch up with Team A because they are 2 hours behind and are traveling at the same speed. Okay, so if you were to graph that, those two lines would be parallel to one another because they have the same rate of speed, which is the slope. Okay, so there is no way that Team B will be able to catch up with Team A. All right, and that is solving systems of equations with special situations.